Hello wonderful people, it's Medicosis Perfectionalis. Welcome back to my chemistry playlist. In previous videos we talked about elements and the periodic table of the elements. We talked about atoms and the subatomic particles, the neutrons, the protons, the electrons. We talked about the 4 quantum numbers. We talked about the types of chemical reactions, the types of chemical bonds, chemical thermodynamics, chemical kinetics, chemical equilibrium. This is our third video on stoichiometry. We talked about ideal stoichiometry and then limiting reactant stoichiometry. And then let's take it to the next level and talk about solution stoichiometry. We are going to use this formula today. M1V1 equals M2V2, where M is the molarity, which is a measure of concentration of the solution, multiplied by the volume of the same solution, equals M2V2. As always, we have many practice problems, so grab a sheet of paper and let's see how many you will answer correctly. Click the like button, click the subscribe button, and let's get started. This is my chemistry playlist. Please watch these videos in order for maximum understanding and retention. After the success and the popularity of my previous videos on stoichiometry, especially the first one, which is epic, it was about ideal stoichiometry, where everything is hunky-dory, nothing is going to run out. But limiting reactant stoichiometry, we are limited by one of the reactants, which will run out sooner than the other. Ideal stoichiometry is in ideal conditions. I do not run out of any ingredients. There is no loss of reactants. And 100% yield for the products will be achieved. No waste, 100% efficiency. Of course, this is la-la land that does not exist in reality. What does exist in reality is limiting reactant stoichiometry. This is more realistic because some reactants go through the chemical reaction, yielding products. So the yield is not 100%. We did not start with enough ingredients, so one of the reactants will run out first, making it the limiting reactant. Stoichiometry skills. You need to balance the chemical equation. If it's not balanced, you're toast. Make sure that you have all the coefficients that you need. Figure out how to create a mole ratio between any two items. Could be between a reactant and another reactant, or between a reactant and a product, or between a product and another product. Ideal stoichiometry problems come in only 4 flavors: mole to mole, mole to mass, mass to mole, and mass to mass problems. The first one takes 1 step to answer. The second and the third each takes 2 steps to answer, and the last one is the most horrible, takes 3 steps to solve. Refer to my video titled Ideal Stoichiometry to learn more. You can find it in this chemistry playlist. As for the limiting reactant stoichiometry, we had 5 types of problems. Please refer to the previous video. If you want to download these doozy colorful notes, go to medicosisperfectionalis.com. I help you learn, understand, and pass exams. If you want me to personally tutor you, reach out to me on my website. Today we're talking about solution stoichiometry. We have 3 flavors of problems. Number 1, they're going to ask you to find or to calculate the volume, which takes 3 steps, or you can use M1V1 equals M2V2, but be careful of the coefficients. Stoichiometric coefficients, that is. The second flavor asks you about the concentration or the molarity. Please calculate the molarity, which is moles per liter. Remember that molarity is per liter, but molality is per kilogram. The third flavor is to ask you about the mass. Also 3 steps, but here you will need to figure out the molar mass, which means that you will need to look at your periodic table, not at the atomic numbers, but at the mass numbers, the bigger numbers. For example, the mass number of sodium is 23, not 11. 11 is the atomic number of sodium, but 23 is the mass number of sodium. 23, the mass number, is the one that we will care about to calculate the molar mass. Some of today's problems will be ideal, some of them will be a limiting reactant. Please remember that when you add a solute to a solvent and then stir, you create a solution. If you wish to see more videos like this in the future, please drop a test tube emoji in the comments. Question: what do you call a test tube that has finished its education? A graduated cylinder. What is the anatomy of the chemical reaction? You have reactants on the left, products on the right, with an arrow in between. Make sure that the chemical equation is balanced. Here I have 1 silicon, here I have 1 silicon. 4 chlorides, how about here? 4 chlorides. 6 hydrogens, here I have 2 and 4, 6 hydrogens. 3 oxygens, yes indeed 3 oxygens. This equation is more balanced than the government's budget. Next, how do we create a mole ratio? Here's this equation. Let's call this A, let's call this B, let's call this C, let's call that D. You can relate A to B. This is A and this is B. Notice that I have 6 moles of A and I have only 1 mole of B. These are called stoichiometric coefficients, 6 and 1 respectively. So this is how you create a mole ratio for these two. You can also relate A and D together. Here is A, here is D. I have 6 moles of A and only 3 moles of D. There you go. We call it mole ratio for an obvious reason. You have moles in the numerator and moles in the denominator. You can relate B to D. Here is B, here is D. Stoichiometric coefficient is 1, but here is 3. There you go, 1 over 3. You can relate A to C, 6 and 2. There you go. You can relate B to C, 1 to 2. Amazing. Last, C to D, and this is 2 over 3. Easy peasy, lemon squeezy, medicosis schmeezy. Let's practice what we preach. Here's the first problem. What volume of 0.2 molar potassium chloride solution is going to fully or completely react with half a liter of 0.4 molar lead Roman numeral 2 nitrate solution? Please pause the video and try to find a solution to this problem. See what I did there? Step number 1, write down the balanced chemical equation. They said potassium chloride, so you write potassium chloride. Make sure you wrote it correctly. Potassium is 1, chloride is 1, so there is 1 here and 1 there. You don't have to write them. We're going to react this with lead 2 nitrate. They already said that the lead is 2, okay. And nitrate is always 1. So therefore, there is 1 under the lead. You don't have to write it. But there is 2 under the nitrate. You do have to write that. And give me your Cupid arrow. And then let's find the product. Well, this is a double replacement or double displacement reaction. So the K will pair with the NO3. And as you know, K is 1. NO3 was 1. So there you go, 1 and 1. We do not have to write anything. Next, the chloride will pair with the lead Roman numeral 2. So it is Pb, but this is 2. And chloride is always 1. So it is PbCl2. Is this equation balanced? Well, let's see. I have 2 chlorides on the right, but only 1 on the left. So you multiply this by 2. I have 2 potassiums on the left and 1 only on the right. So you put 2 here. Now it's 2 potassiums, 2 potassiums. 2 chlorides and 2 chlorides. How about this? Well, I have 1 lead and 1 lead, so that's okay. And then you have 2 nitrates. Here you have 2 nitrates. Bingo, the equation is balanced. Then with stoichiometry, you always start with what you have. What do I know the most about? When it comes to potassium chloride, I only know the concentration or the molarity. But when it comes to lead 2 nitrate, I have the volume and the molarity. So you start with what you know the most. So I'm gonna start with lead nitrate. They want the volume from me, and I start with what I know, which is lead nitrate. Let's start with its molarity. Remember that molarity is moles per liter. So you write it like this, 0.4 moles of PbNO3 multiplied by 2. All of this is over liter because molar or molarity is moles per liter. And then you multiply this by the volume. The volume of lead 2 nitrate is half a liter. You put half a liter upstairs and you put 1 downstairs. You cancel the liter with the liter. Then I want to put moles of PbNO3 in the denominator so that I can cancel this with that. So you put mole of PbNO3 all by 2. And upstairs, what do you put? We're trying to do a mole ratio. Between what and what? Between the 2 reactants. You have 1 mole PbNO3, so you put a 1 right here. But you have 2 moles KCl, you write this up here, okay? Now if I cancel moles PbNO3 with moles PbNO3, my answer will be in moles of KCl. But I do not want the number of moles of KCl, I want the volume of KCl. So there needs to be another multiplication, and this multiplication has to have moles of KCl down here, and it has to have liters up here. What should I do? You see this? 0.2 molar means 0.2 moles per liter. So this is 0.2 moles downstairs and only 1 liter upstairs. 0.2 moles per liter. Now we are confident when you cancel moles of potassium chloride with moles of potassium chloride, and then you just calculate 0.4 times 0.5 times 2 times 1 divided by 1 times 1 times 0.2 when you multiply all of these together, what do you get? You get 2 liters, because this is the liter that's left. 0.4 times 0.5 times 2. 2 times half is 1. Times 0.4 is 0.4 in the numerator, divided by 0.2 in the denominator. 0.4 divided by 0.2 is 2 liters. And this is how you find the volume of potassium chloride, or KCl. Bingo, done. It took us 3 steps, as you see. Is there another way to solve this? Absolutely. It's the famous M1V1 equals M2V2, but we gotta be careful. M1V1 belongs to KCl, M2V2 belongs to PbNO3 all by 2. Okay, then what? You gotta be very careful with the mole ratios. You see 2 here, and you're gonna do crisscross. This 2 is gonna go here, and this 1 is gonna go here. Okay? And then what? We want the volume of potassium chloride. Potassium chloride is 1, so you want V1. This is the unknown, so therefore you say the following. V1 equals, by dividing both sides of the equation by M1, you get the following. You get 2 M2V2 divided by M1. Okay, so 2. And what is M2, please? M2 is the concentration of this lead 2 nitrate, and its concentration is what? 0.4 molar. You plug in this here, and you multiply this by V2. V2 is the volume of lead 2 nitrate, which is 0.5 liters. All of this is divided by M1, which is the concentration of KCl, which is 0.2 molar, like this. You can cancel molar with molar. 0.5 times 2 is 1, times 0.4 is 0.4. 0.4 divided by 0.2 is simply 2 liters. I got the same answer here as in here. Pay attention. If you use V2 as liters, V1 will be in liters. But if you plug in V2 in milliliters, then V1 has to be in milliliters as well. Putting V2 as milliliters and expecting V1 to end up as liters is the definition of insanity, as Einstein once said. Here's the same answer in more color. Notice it took me 3 steps. You can also try the second method, which is M1V1 equals M2V2, but be careful with the coefficients. The 2 KCl will go here, and the 1 PB will go there. Some crisscross action. This was the first situation, which is what is the volume, and it took us 3 steps, or simply using M1V1 equals M2V2. Next, what is the concentration or the molarity? So let's practice. Oh, this one is going to ask you about the molarity. If 100 ml of 0.3 molar Ki solution is needed to completely react with 50 ml of lead 2 nitrate solution, what was the initial molarity of the lead 2 nitrate solution? Pause the video and try to solve this yourself. Step number 1, give me the balanced chemical equations. You start with the Ki, which is potassium iodide, and we're gonna mix this with lead 2 nitrate. It's lead 2, mind you, so this is Pb, and it's 2, and nitrate is 1, so there you go. 1 does not have to be written, but the 2 has to be written for sure, just like the previous question. And this shall yield what? It's a beautiful double replacement or double displacement, so the K is gonna kiss the NaO3 like this, and the lead is going to copulate with the iodide. It's not a good idea to teach chemistry just after biology, just saying. Remember that your lead is Roman numeral 2, and the iodide is always 1. So 1 does not have to be written, but the 2 has to be written for sure. So now we're good to go, right? Shut up. You need to balance the equation first. How many iodines you have on the right? You have 2, and on the left 1. So multiply this by 2. How many potassiums on the left? 2, and on the right? Oh, you gotta multiply this by 2. How many nitrates on the right? 2, and on the left? 2. Good. How many leads on the left? 1, and on the right? 1. Beautimous. So step number 1, write down the equation. Step number 2, balance the equation. Step number 3, start your stoichiometric magic, beginning with what you know the most about. I know the most about Ki because I have the volume and the concentration. So let's start with Ki. Remember that molarity is moles per liter, so you say that 0.3 moles of Ki per liter, because this means 0.3 molar Ki multiplied by its volume, which is 100 ml. Convert that to liters, to get 0.1 liters divided by 1. And then you multiply me one more time by, well, I'm going to cancel the liters with the liters. I need to cancel moles Ki with moles Ki. So you put mole Ki down here, and you use the mole conversion ratio or the mole ratio. How many mole Ki's do you have here? I have 2. And how many moles PbNO3? I have 1. There you go. You write it down like this. Okay, and then what should I do? After this, you're gonna cancel mole Ki with mole Ki. What am I trying to achieve? You're trying to find the molarity of lead-2 nitrate. Oh, so molarity is number of moles per liter. So I need liters in the denominator. And they already gave me 50 mLs of lead-2 nitrate. 50 mLs, convert that to liters by dividing by 1,000. 50 divided by 1,000 is 0.05 liters, and there is just a 1. The numerator has 0.3 multiplied by 0.1 is 0.03, and that's the numerator. As for the denominator, it has 2 times 0.05 is simply 0.1. When you divide something by 0.1, it's as if you're multiplying by 10. So 0.03 by 10 is simply 0.3. 0.3 what? Moles per liter, or simply molar. Molar of what? Of PbNO3, which is exactly what I want. Okay. And is there another way to solve this problem? Absolutely. And this is the famous M1V1 equals M2V2. But let's say what we're talking about. M1V1 is for potassium iodide. M2V2 is for lead-2 nitrate, just like that. Be very careful with the stoichiometric coefficients, and you need to do the crisscross action. The 2 goes here, and the 1 goes here. You do not have to write the 1. What do you want? I want the molarity, which is the concentration, which is the M of what? Of lead-2 nitrate. So I need the M2. So let's rearrange the equation to say that M2 equals, by dividing each side of the equation by 2V2, there you go, 2V2 down here, and M1V1 up here. Okay, M2 equals, M1 is what? M1 is the molarity of Ki. It is 0.3. Amazing. We're going to multiply the 0.3 molar by V1. V1 is the volume of Ki, which is 100 mLs. You can leave them as mLs because you'll have mLs in the denominator and the numerator, so they will cancel one another. So this is the 100 mLs. Divided by 2 multiplied by V2, which is the volume of the Pb nitrate. And this is 50 mLs. You put that down here. And then don't forget to cancel mLs with mLs. You cancel the 0 with the 0. 0.3 times 10 is 3. 3 divided by 10 is 0.3. 0.3 what? 0.3 molar. This answer is identical to this answer. Here are the same answers in color. The method number 1 is basically to cancel up and down together. Notice that it took us 3 steps. You want your measuring unit in the final answer to be in moles per liter. Moles per liter. Method B is M1V1 equals M2V2. Don't forget the crisscross action. Idea number 3. What is the mass? And to figure out the mass, still 3 steps, but you will need to figure out the molar mass in order to find the mass. Molar mass is measured in grams per mole. Mass is measured in grams. And to find the molar mass, you need to bring your periodic table with you. Problem number 3. What is the mass in grams of calcium hydroxide that is needed to neutralize 500 ml of 0.2 molar HNO3? Pause the video and get comfy. Step number 1. Write down the equation. Okay, calcium hydroxide. So let's write that down. There is CaOH2. Okay, and this is going to react with what? It's going to react with HNO3 and then yields double displacement. Calcium is going to kiss the NO3. Calcium, if you remember, is divalent, so this is 2. As for the NO3, it is monovalent, so basically it is CaNO3 2. Then the hydrogen will hug the hydroxide to make what? To make water, H2O. Step number 2 is balance the chemical equation. I have 1 calcium on the left and 1 calcium on the right. Beautiful. I have 2 nitrates on the right, and on the left I have only 1, so you multiply by 2. Amazing. Let's count the hydrogens. On the left I have 2 hydrogens and 2 for a total of 4 hydrogens. But on the right, I only have 2 hydrogens, so you multiply that by 2. Now let's count the oxygens. 2 oxygens plus 6 oxygens is 8. 6 oxygens and 2 oxygens also 8. The equation is balanced. What should I do? You should start by what you know. What do you know the most about? I know the most about HNO3. I know its volume and its concentration. Start with the concentration like this. 0.2 moles per liter. Here's the moles, here is the liter. Moles per liter of what? Of HNO3. Amazing. You multiply this by its volume. And its volume is 500 mLs. Convert that to liters by dividing by 1,000, or 0.5 liters divided by 1. Cancel liters with liters. I need to put moles of HNO3 in the denominator. Give me the mole ratio. So you put mole HNO3 in the denominator to cancel with the numerator. How many moles HNO3 here? We have 2, so you write 2 here. And you have only 1 mole of calcium hydroxide. Okay. Then what do? I can cancel the moles of HNO3 with moles of HNO3. But the answer has to be in grams. And I see no grams in sight, unless I go to the periodic table and find the molar mass. The molar mass of what? Of calcium hydroxide. So basically, I need to find the molar mass of calcium hydroxide. Now I'll be able to cancel the calcium hydroxide on this side with mole calcium hydroxide on that side. Okay? Go to the periodic table. What do I need? I need calcium, and I need OH multiplied by 2. According to my periodic table, the mass number of calcium is about 40 or 40.1. Oxygen is 16. Hydrogen is 1. 16 plus 1 is 17. Multiply that by 2 and you get 34. Then you add 40.1 to 34. 4 plus 0 is 4 and 3 plus 4 is 7. So 74.1 what? Grams per mole. Grams per mole. And now when we do the math, after canceling everything except grams, you will find that your answer will be in grams, which is exactly what we want. 0.2 times 0.5 is 0.1. 0.1 times 74.1 is 7.41 grams divided by the denominator only has a 2. Just like this, 7 divided by 2 is 3.5, and the 40 divided by 2 is 20, so this is about 3.71 or 705 grams as my final answer. Grams of what? Grams of calcium hydroxide, to be exact. So to find the mass in grams in solution stoichiometry, you need 3 steps as you see, the last of which is to find the molar mass using the periodic table. Notice that the HNO3 could be thought of as the limiting reactant. But in the next example, I will have no idea what the limiting reactant is. If you have watched my previous video on limiting reactant stoichiometry, I've told you that we have 2 methods to find the limiting reactant. You can use method A or guess what? Method B. In method A, you begin with both reactants and aim for one product, for the same product each time. The reactant that will give you less of the products is the limiting reactant. Less is limiting. But the reactant that will give you more is the excess reactant. Method number B is you choose only one reactant and assume that it's the limiting reactant, and then convert to the other reactant, not product. And after this, evaluate. Do I have more than I need, or do I need more than I have? If you have more than you need, then therefore you guessed correctly, voila, and you're done. What you guessed in the beginning is the actual limiting reactant. But if you need more than you have, then you guessed incorrectly, and therefore the other reactant is the actual limiting reactant. If this sounds insane to you, please refer to my video on ideal stoichiometry. You can find it in this chemistry playlist. Example number 5. A volume of 50 mL of 0.25 molar calcium chloride solution was mixed with 100 mL of 0.2 molar sodium phosphate solution. Please calculate the mass of solid calcium phosphate that can be produced. Okay, step number 1 is to write down the chemical equation and to balance it. So, what do I start with? They said calcium chloride, right? Calcium chloride. Calcium is divalent, chloride will give me 1, so this is CaCl2. Then I'm gonna react with sodium phosphate. Here is sodium, that's monovalent for sure, and then phosphate like this. Phosphate has a number of 3, So 3 will be under the sodium, and under the PO4 is just 1, so there is no need to write the 1. Then the lovely double replacement or double displacement, the Ca will hug the PO4. Ca is divalent, PO is 3, so be careful with this. So there is Ca, and this is divalent. PO4 has a number of 3, so it is Ca3PO4 all 2. This is the calcium phosphate that they are crying about. Then the sodium will hug the chloride as they always do, giving me the famous sodium chloride. This is 1 and this is 1, so we are done. Next, I need to balance this puppy. Okay, I have 2 chlorides on the right, then multiply this by 2 to have 2 chlorides on the left. Now I have 2 sodium on the right, but 3 on the left. Whenever you encounter 2 on one side and 3 on one side, you multiply the 3 by a 2, and you multiply the 2 by a 3, so it becomes a 6. Are we done? Not really. I have 3 calciums on the right, so you multiply this by 3. So let's see. I have 3 calciums on the left, 3 calciums on the right. 6 chlorines on the left and 6 chlorines on the right. 6 sodiums on the left and 6 sodiums on the right. 2 phosphate groups on the left and 2 phosphate groups on the right. Beautiful. Then what should we do? Be careful. We have no idea which one of these 2 is the limiting reactant. It could be this or it could be that. Whoever is the limiting reactant will give us less of calcium phosphate. So we need to try with both. I'm going to use method A, so I'll start with calcium chlorides and aim at calcium phosphate. Then I will do this again, starting with sodium phosphate and aiming at calcium phosphate. Let's start with calcium chloride. What do you know about it? I know it is 0.25 molar, which means 0.25 moles of CaCl2 divided by liters, multiplied by its volume, 50 mLs, divided by 1,000 is 0.05 liters, divided by 1, cancel liters with liters. What do you want next? I want to put moles of calcium chloride in the denominator, just like that, okay, and use the mole ratio. Calcium chloride here is found 3 times, and what are you aiming at? Calcium phosphate. It's only 1 mole of Ca3PO4 all 2. And then you multiply. By what? I'm trying to find the mass. Oh, you're trying to find the mass of Ca3PO4 that will produce. That's correct. So therefore, I need the periodic table to tell me the molar mass of calcium phosphate, or Ca3PO4 all 2. Let's go to the periodic table. Calcium is 40.1, and we're going to multiply this by 3. Plus, each oxygen is 16, times 4 is 64. Phosphorus is 30.97. Add that to the 64, and you get 94.97. Multiply all of this by 2, and you get 189.94. You write this right here, and then we're going to multiply 40.3 by 3, and this is 120.3, plus 189.94 equals 310.24 grams, of course. I forgot to cancel moles CaCl2 with moles CaCl2. Cancel mole calcium phosphate with mole calcium phosphate, and my answer will be in grams. Then you do the math for all of this, and you get an answer of 1.29 grams. This is for the reactant calcium chloride. Let's try the whole thing for the reactant sodium phosphate. Sodium phosphate, what is your concentration? 0.2. So it is 0.2 mole sodium phosphate Na3PO4 divided by liter. And what's your volume? My volume is 100 mLs, which is suspiciously equal 0.1 liters divided by 1. And then cancel liter with liter. I need the mole ratio. You put mole of Na3PO4 down here, and you look at the equation. You had 2 moles NO3, and what are you aiming at? I am aiming at calcium phosphate. I have 1 mole Ca3PO4 all 2. Then you need the periodic table to find the molar mass of calcium phosphate, which is the goal. I've already calculated this to be 310.24 grams in each 1 mole of calcium phosphate, like this. And then we cancel. We cancel moles Na3PO4 with moles Na3PO4. Cancel mole calcium phosphate with moles of calcium phosphate and your answer will be in grams. And the final answer for this nonsense is what? It is 3.1 grams. Then ask yourself, out of these two, which one is the lower? Of course, 1.29 is less than 3 grams, making the first one, which is calcium chloride, the actual limiting reactant. So the actual answer for this is 1.29 grams of calcium phosphate. And this is what will be produced. And this is my final answer. Here is the same answer in more color. You start with the first reactant and aim at the product that they want, which is calcium phosphate, and you find your answer. Then you start with the second reactant and aim at the same product and find your answer, and you're gonna choose the lesser of two evils. And this will be the limiting reactant. If this was ideal stoichiometry and I will not run out of anything, I will produce 3.1 grams. But because life doesn't always give you what you want, hashtag limiting reactant stoichiometry, this is what you get. And 1.29 grams of calcium phosphate is the final answer. Question number 5, please pause the video. You should be able to solve this in less than 15 seconds. Let me know your answer in the comments. Remember that molarity is number of moles of solute per liters of solution. To learn more about solution, please watch my previous videos. You can download my notes at medicosisperfectionalis.com. I have notes for general chemistry, organic chemistry, biochemistry, physics, biology, anatomy, physiology, you name it. Help me make more videos by supporting the channel. Go to buymeacoffee.com/medicosis. If you want to learn about metabolic acidosis and alkalosis, respiratory acidosis and alkalosis, anion gap, osmolar gap, and more, download my acid-base course at medicosisperfectionalis.com. It comes with videos, notes, and cases. There are more than 600 premium videos available on this channel when you click the join button and choose the highest tier. Please subscribe, hit the bell, smash like, support my channel on Patreon, PayPal, or Venmo. Go to my website to download my courses, notes, and cases, or if you would like me to personally tutor you. Be safe, stay happy, study hard. This is Medicosis Perfectionalis, where medicine, chemistry, math, and physics make perfect sense.